All right, testing, testing. All right, to those of you who navigated to this video, thank you very much. We really appreciate it. What we're going to show you today is an example of our optimization script that we wrote for Galapagos and Grasshopper 3D using Rhinoceros. Grasshopper is a plugin, it's a parametric plugin that we use to do some design with respect to data sets and how we take our coordination of buildings and build them a little smarter. If you read the white paper, you know that we did some cool stuff with laser scan placement, and what we're going to show you right now is kind of how the script runs and the process that we go through to get it. So this is the script. It's not too big. We've put a lot of thought and a lot of effort into it, our inputs and our outputs. And this is an example of an optimized solution from Galapagos and Grasshopper. If you see if I pick a curve, one of our exclusion curves, and I move it, we don't want to be scanning in this spot, and so it eliminates that area. What we'll do is we're going to open up Galapagos and run the solver so you guys can see where it would start from. What it's going ahead and doing here is it's throwing a lot of different options out there, and it's getting a return of what the best area is for the least amount of scans. And once it finds a good one, a local maximum, if you're a stats person, it saves that local maximum, and once it goes through another set of minimums and maximums, it will save out the best maximums, which is the most area for the least amount of scans that we have, and it will then start comparing those. So it's really what it comes down to. It's a very simple search algorithm, but we're using it with respect to spatial arrangements as well as size, and we hope to get a really good solution from that. I'll show you guys real quick. This is the most recent quote-unquote local maximum we have. So that's the best. That's kind of the best fit right now when we talk about fitness of a solution. And that's, if we get a better one, it'll substitute the better one for this one in what we've got. So ultimately, the output here is the XYZ coordinate tied to control of each of these center points, which is really what we want, because that'll tell us, hey, put the scanner right here, and you'll do the least amount of scans. You'll get the best possible area, and you'll get the best possible overlap from a detail standpoint. All right, I'm going to go ahead and hit pause so you guys can see what happens a little further along. So here real quick, you can see on our Galapagos editor that we've got a line of best fit right here, along with deviations on top and bottom, and you can see how it's trending up, is that every time it does a search, it finds a better maximum. You can see it just shifted to a pretty good one right there. I think that's actually one of the better ones we found. And so you can see that it's going to keep searching, and we can actually take the best, kind of what they call the genome, the best, genome is probably the best word, that we have, the best fit so far. We can do what's called a reinstate, which we can say, hey, find me a bunch of other good solutions that are in or around this, because this is a good one, and it'll kind of feed that good gene back into the gene pool. It's really an evolutionary growth algorithm, which is, it's just a little bit more complicated. It takes search algorithms and makes them a little bit more complicated. So I hope you've enjoyed this. There's a lot of really good potential in this. It applies to more than just the laser scan. So make sure you read our next white paper, because we've got some good stuff coming out. All right, thanks guys. Bye.